So good afternoon, everybody. I hope you can hear me. I'm guessing that you can hear me. Please, anyone send me a reply, open the mic, and just tell me if you can hear me.
Yes.
Perfect. Thank you very much. Okay, it's almost 2 o'clock. We should wait 1 more minute just to make sure that everybody is wants to attend. It's already online. I will share my my screen with the presentation. See that this is not quite okay. Let's see. Again, not okay. I should share screen one. Yeah. Can you see my presentation in full, or most probably you cannot?
No, it's not in full.
I'll do something else then. Perfect. Now most probably you see it in full. That's great.
But you switch it off.
Yeah, of course.
Okay, now it's on.
Okay, so just some technical information. I want to announce that this meeting will be recorded and will be available on the Probe YouTube channel. Good afternoon, first of all. My name is Livio Belegante. I work at the National Institute of Research and Development for Optoelectronics in NOE as a senior scientist working on active remote sensing, mainly with Lidars, and together with Horatiu Ștefănie from the Babeș-Bolyai University in Cluj, we had prepared an introduction course. One second, okay. On LiDAR instruments and products. This course aims, of course, new LiDAR operators and scientists that are not so familiar with LiDAR instruments, the measurement procedures that we apply mainly in the ACTRIS research infrastructure, the alignment of LiDAR instruments, of course, also the quality assurance procedures that we apply to make sure that the data that we collect has a certain high quality, and also are not familiar with data flows and processing the processing of the LiDAR using the single calculus chain. In other words, I would say that The course will act as a practical guide for new users on how to prepare a LiDAR instrument and how to operate the LiDAR station. The course is mainly focused on a short introduction to LiDAR instruments. Here I will give a short overview of how a LiDAR instrument works, several types of LiDAR instruments, and according to your feedback, I will move on or discuss more about this, let's say, main or fundamental topics. I will give some examples from the Romanian LiDAR sites on LiDAR instruments, and I will then get into details on the initial setup of the LiDAR instrument. Then we'll discuss about the quality assurance criteria and the tests that we need to perform to make sure that a LiDAR instrument works accordingly and works as we should expect. And then we'll focus on the data processing procedures. And here I'm referring mainly to the ACTRIS Single Calculus Chain initial setup, because this setup is quite demanding and requires the user to, let's say, to know a lot of information on the LiDAR instruments that they want to use, and on the products that they want to get out of these LiDAR instruments. Of course, we also must discuss about the data formats, because it's not easy to, or not straightforward to send this LiDAR data to the single calculus chain. And since we need to optimize the data transfer and the data processing, we'll discuss about some tools that you can use for data transfer. As already stated, the purpose of this course is to have just an introduction on LiDAR instruments and products. So you'll not know everything, but you'll only have an idea. You'll have a very clear idea of what you need to do. We'll also discuss the setup, the initial setup of the instrument. And here I'm referring to the optimization of the signal, because once you have the signal, you need to optimize it so you have a very good LiDAR product. And of course, as stated before, the data processing. And this mainly aims LiDAR stations, new LiDAR stations, and operators applying as a national facility in the framework of CARS, which is part of the ACTRIS research infrastructure. And if you want to know more, you can access the ACTRIS official website, and I'm sure that if you need more information, you can contact any ACTRIS representative. Based on this course, the operators will be able to initially set up the LiDAR instrument, perform and check the quality assurance tests required to operate within the ACTRIS research infrastructure, and not only. It's good to follow these rules even if you are not an ACTRIS research infrastructure. Pre-process the quality assurance tests, because we will require a certain format, because these quality assurance tests need to be submitted to the CARS center facility. so that each station and each LiDAR unit gets thumbs up flag that everything works correctly. Then, based on what you'll hear today, you'll be able to set up the single calculus chain and most probably deal with possible errors that you will encounter. And last but not least, you'll be able to submit the LiDAR data to the single calculus chain in an operative way, so that you will use different tools and scripts to prepare and send the data. Some technicalities. The course will take around 3 to 4 hours maximum, depending also on your feedback, of course. Each main section, I would say that will take around 50 minutes, and I'm planning to have a more or less 10 minutes break after each section. But if you feel the need to have a technical break, please stop me at any time, and we can have this break. Of course, after each subsection, and not only, the participants are invited to ask questions and discuss on the topics that the course is on, but not only. If you have also other questions that are, let's say, not directly related but are important for you, please do not hesitate. So let's start the course, introduction on LiDAR instruments. So we are talking about LiDAR instruments, but of course we need to understand what's a LiDAR instrument. LiDAR comes from light detection and ranging. And after searching the internet and all of the sources that I have on what is officially defined as a LiDAR, we found several descriptions. So first, which is found on the wiki page, is that a LiDAR, it's a method for determining ranges by targeting an object with a laser. From the faculties, different faculties and universities, I received the information that this LiDAR, it's an instrument similar with radar, sorry, not LiDAR, but uses the light, the laser light, instead of microwaves. And this is a more clear, let's say, overall hint on what's a LiDAR instrument. The main difference between the LiDAR and the radar, first, it uses a different wavelength, and second, most LiDAR instruments, especially the one that we will discuss about, are pointing in one direction and are collecting information from one direction. Usually the radar is scanning. It's a scanning instrument that circles and looks at a certain area. So mostly this is the difference between LiDAR and the radar. I would say that also the third description, it's quite accurate. So it's a remote sensing method used to examine the surface of the Earth. And here, this description is mainly focused on a certain type of LiDAR, but we can extend it, and we can say that it's a remote sensing method used to examine different layers, atmospheric layers, or hard target layers like the Earth's surface. And the fourth description could be something like LiDAR. It's an instrument that is using laser light to study atmospheric properties, usually from the ground up to the top of the atmosphere. So this is on the atmospheric LiDAR topic found all over the web. So we can see that according to the descriptions, we have many type of LiDAR instruments. And these instruments are used for different applications. Can you see my mouse pointer? Yeah, okay, perfect. So you can see my mouse pointer. Usually, I would say that LiDAR instruments are instruments that are using remote sensing techniques by emitting a laser pulse. This is done in the emission unit. What you have here, shown with my mouse pointer, is the emission unit. This unit is made up of laser and usually some optics that are used to optimize the laser light and to direct the laser light towards the target of interest. In our case, the atmosphere. What happens next? In the atmosphere, this laser light encounters different scatterers like molecules or aerosols or clouds or water droplets and so on, and this light is scattered on these particles, on these scatterers, let's say. And next part, of course, part of this this light is reflected backwards. It's reflected in an elastic by an elastic reflection, or let's say a Raman reflection. So inelastic reflection, and this light is collected by what we call the receiving unit. The receiving unit, usually in a LiDAR system, is made out of telescope that is used to collect the light, focus the light, and direct the light to the so-called wavelength separation unit. This unit is made up of several optical components that are doing special filtration to the received light. So these optical components are filtering the light and focusing the light towards the detection units, which are in our case usually PMTs, photomultipliers, APDs, or photodiodes, and of course CCDs. And CCDs, I will not have to explain what's a CCD. So this is more or less what happens when we use a LiDAR system. What's important about this technique is that the laser light emitted is not a continuous pulse, but short pulse laser light, because the LiDAR system is actually ranging the scattered light collected by the telescope. This means that for every altitude section, the LiDAR unit will collect and will know that a certain amount of light comes from that specific altitude. So after measuring or operating a LiDAR unit, we will obtain a profile of backscattered light in this case. I don't know if it's clear, so if this, let's say, main principle is not clear, please stop me and I will get into more details. If not, I will move on. Okay. So as I said, regarding the components, a LiDAR instrument is made up of an emission unit, which has a laser unit and steering optics, a receiving unit made up of a telescope, the wavelength separation unit that is composed of filters, mirrors, lenses, polarizers, according to exactly what we want to measure, the detectors, as I said, the PNT, the APD, or even CCD, and the digitizers, which are the electronic units that record the LiDAR signal coming from this detectors. Now let's go towards the type of LiDAR instruments that we can find, let's say, mostly in our research area. Of course, these are not all the LiDAR instruments that you will find. If I were to think what is a LiDAR instrument, I would think firstly at an instrument used used by the cops, for example, to measure the speed of my car. And this is also a LiDAR instrument. So we have several more LiDAR instrument types, but we will focus on the main ones that we would use or could use in the future in our research activity. So the first type of LiDAR instrument is the topographic or the scanning LiDAR instrument. And this is used to examine distances to surfaces or used to examine especially surfaces, so the shape of a surface. The second one, which is similar with the topographic, is the backscatter LiDAR instrument. And in our case, this LiDAR instrument is used to study suspended particles. And here I'm referring to molecules, aerosols, and even droplets, let's say. The third type of LiDAR instruments that we are really interested on is the Deprivation LiDAR instrument. And this LiDAR is used to study the shape of particles. In other words, by looking at how these particles are changing the depolarization state of the emitted light, we can retrieve information on the shape or the anisotropy of the atmospheric particles. Since I know that most of the participants to this course are not really familiar with LiDAR instruments, I will get a little bit into details about what is this depolarization. Usually, the emitted laser light used in this type of LiDAR units is linearly polarized. So the emitted laser light is fully polarized linearly. So this means that only one component of the parallel and cross, let's say, components is emitted. On the interaction with the atmosphere, this linearly polarized laser light can be depolarized based on the shape of the scatterers, in our case, the aerosols. And once we collect the backscatter light coming from these particles, we can look at how much of this initially polarized light was modified. And we can do this by looking at the initial, and we call it the parallel component of the emitted laser light, and the cross component of the emitted laser light. And by comparing the two, we can obtain information on this shape. We will get into details a little bit later, but I wanted to have an initial introduction on this depolarization. Another type of LiDAR instrument is the Raman LiDAR instrument. This is more or less similar with the backscatter LiDAR instrument, with the difference that the emitted light is not reflected, elastically reflected on the aerosols, but is inelastically reflected. So these light molecules are absorbed by different molecules and then emitted back, but inelastically. So we have this inelastic Raman phenomena that is taking place during this, let's say, scattering. So we actually emit a certain wavelength and we collect a different wavelength. And usually the Raman is focused on specific molecules, because obviously molecules are absorbing certain type of light, a certain type of light, and emits a certain type of light that is specific to that molecule. I would say, as an example, that we use, for example, the 355 light, and while and on the interaction of the nitrogen, the emitted Raman light is 387, and we collect the 387 nanometers light. But we will get into more details once we move further on. Another type of LiDAR instruments is the wind LiDAR, which uses the Doppler effect to determine the wind profiles, the vertical wind profiles of the atmosphere. The high spectral resolution LiDAR is a special type of LiDAR that is able to look and separate and to distinguish between the scattered light coming from the aerosols and from the molecule. And so it's able to distinguish between these two, but we will not get into much details about this high spectral resolution LiDAR, because we need mostly to focus on our, let's say, field of application. Another type of LiDAR instrument is the dial. This is a differential optical absorption LiDAR, which is used to retrieve the concentration of atmospheric species, so the molecules. And the last type of LiDAR, I would say, that is the fluorescence LiDAR, is used to detect fluorescent components from atmospheric constituents, or from water, or from vegetation, and so and many more, depending on what we are interested on. Of course, in our let's say practical guide, we'll focus on the backscatter, on the depolarization, and on the Raman LiDAR instruments. As I said, since we are focused on this type of LiDAR instruments, the channels that we will look at are the elastic channels. And here, when I say elastic, I'm referring to the fact that the emitted laser light is similar with the collected laser light, so wavelength. So for example, if I use a Yagni-Odin laser that is emitting at 164 nanometers, I will collect also the 164 nanometers. If I'm using the laser light to emit the 532 nanometers wavelength, I will collect also the 532. So this is why it is called elastic. Elastic depolarization is exactly what I said a little bit earlier. So I'm emitting, of course, the 532, but I'm emitting only the, for example, parallel component, and I'm collecting both the parallel and the cross component. And if I manage inside the wavelength separation unit to separate these components and detect them separately, I am able to look at this depolarization. The third type of channel is the Raman, that could be vibrational or rotational. The Raman means that the laser light emitted is different than the wavelength of the laser light collected by the LiDAR unit. So, for example, if I emit the 532 nanometers laser light, based on the interaction with nitrogen molecules, I do not collect the 532, I collect the 607 nanometers laser light. Yeah, so the nitrogen molecules, we can say that it keeps a part of the energy of the laser light. Okay, so it collects 607. These three channels are the main channels that we are interested on, and these are the channels that we will set up inside the single calculus chain. Now I will give some examples on the channels that we find and we use for our LiDAR instrument, the LiDAR instruments from Cluj, and the NAOC LiDAR instrument from Czech Republic. In case of INOE, we emit three wavelengths, the 1064, the 542, and the 355. But we collect more, of course, because we also have the Raman and the elastic depolarization. In this case, we collect the 355 total, I would say, total component. So we collect exactly what we emit. We collect the 1064. These are the two elastic channels that we have. But we also collect, we also collect the 607, which is the Raman channel coming from the 532, and the 387, which is the Raman channel the Raman channel, let's say, coming from the 355 nanometers light. In addition, we also have a water vapor channel coming from the 355 wavelength, which is 408 nanometers, and this defines the Raman response for the water vapor molecules. The 387 and the 607 Raman channels are related to the nitrogen molecules in the atmosphere. For the Cluj station, we have similar channels. We have the elastic, the Raman, and also the depolarization, as for Innoe. So also Innoe and also Cluj has two depolarization channels coming from 532 the 532 nanometers. So we can consider that we emit the parallel component of the 532 nanometers, and we collect two components. Initially, we collect the 532 parallel component, and second, we collect the other component, which is a cross component coming from the 532. And this way, we can look at the shape of the particles. For the NAOC, we have the 532 elastic. This means the LiDAR instrument is emitting 532 and also collecting 532. We have a Raman channel from the 355. So the laser also is emitting the 355, but we collect the 387. And we also have two depolarization channels, but in this case, we have the depolarization channels for 387. So we emit the parallel component and we collect the parallel and the cross component. So these are three examples of LiDAR instruments that are similar, but not totally. So we have different channels for different LiDAR instruments. And that's why it's quite difficult to set up a processing chain for all these channels, because a processing chain for all these channels requires information on each channel, requires information on how the light was emitted, what is the state of the light, and here I'm referring to the polarization of the light, and what is the status, what is the polarization of the collected light. So all this information and much more needs to enter when we set up the single calculus chain. And that's why this course, part of this course. Okay, so since it's better to also see some pictures, because a picture is the first thing that remains when we talk about an instrument. We have here several examples of LiDAR instruments that you can find at Innoe and at the Cluj station. I will start with our main LiDAR instrument, which is the Deprivation Raman LiDAR instrument used in EarlyNet. This is the instrument that I was talking about a little bit earlier. The Cluj LiDAR instrument, which is similar with ours, is this LiDAR instrument. And as you can remember when I talked about the channels of these two LiDAR instruments, I told you that these are quite similar. But as you can see from this picture, the instruments are similar, but in a way different. In many ways, actually different. The size of the telescope, the type of the laser, the repetition rate of the laser, and many other optical properties of the laser light. But also, when we think about the receiving unit, so the detectors could be different, the data acquisition could be different, and so on. Other LiDAR instruments that you can see here, on the left upper side, you see a scanning LiDAR unit, which is a backscatter LiDAR. This is a very simple LiDAR because it emits only two wavelengths, but records only the elastic component of the, let's say, scattered light. So we collect the 1064 and the 532, in this case, the total. But the advantage of such an instrument is that we are able to scan. So we are able to point the LiDAR unit towards a certain target and make studies on that certain target. Another type of LiDAR unit is a sort of a continuous low power LiDAR unit that you can see in the left lower part, which is a ceilometer. This LiDAR unit has the advantage of continuous measurements during snow, during, I don't know, wind, during rain. It doesn't matter. This unit is able to measure continuously and to provide, let's say, a full set of data. Usually this type of low power LiDARs have only elastic channels and usually only one channel. But this is sufficient for the temporal coverage of this type of LiDAR instrument. What you can see in the upper part is the wind LiDAR. I will not get into many details about this wind LiDAR. Here you see another scanning LiDAR unit, which is similar with the one that I talked about a little bit earlier, but this LiDAR unit also has depolarization channels. So you see, we have different LiDARs that are similar, but in many ways different. This is a dial LiDAR used to obtain the ozone concentration profiles in the troposphere. So this LiDAR unit is able to retrieve the concentration of ozone from the ground level to up to 10 kilometers with a vertical resolution, I would say, less than 10 meters with a high accuracy. And this type of LiDAR is used in pollution studies. The LiDAR on the left of the dial is fluorescence LiDAR that is we are usually deployed during campaigns, in field campaigns. And this type of LiDAR unit is specialized for, let's say, water soundings. So we usually put this LiDAR unit on a ship, on a cruising ship. We have a steering mirror and, sorry. Sorry, okay. And Sorry about that. Sorry, it was an incoming call. Okay, so this type of LiDAR is used on ships, is placed on ships. We have a steering mirror that directs the laser light towards the water and collects what is reflected on the water surface and several meters below. And this type of LiDAR unit is used to obtain information on the quality of the water. So the information on the dissolved organic matter, on the chlorophyll components, and on the let's say petrol compounds that can be found inside the water. Another type of LiDAR that I would like to present is the high spectral resolution LiDAR. This LiDAR is able to let's say look at the backscattered light coming from aerosol and coming from molecules, and it's able to distinguish between the two. I think we covered more or less all the examples, and if you do not have any particular questions about these LiDAR units, I would move on. So, regarding the configurations of these LiDAR units, of course, as you could see, we have different type of LiDAR units, and even if those are similar, they are in many ways different. And one way in which a LiDAR could be different from another is the emission configuration. So LiDARs could be monoaxial, so we have more or less the same axis for the emitted light as for the telescope, or biaxial, so we have two axes. One would be the emission and the other one the reception. And the advantage of a biaxial system is that it can be used with several telescopes. And this is, of course, my personal opinion, is that with this type of configuration is easier to construct and implement. So, what can we study using a LiDAR instrument? So the LiDAR studies are mostly focused on, of course, aerosols, aerosol cloud interactions, the dynamics of the atmosphere, the planetary boundary layer, and studies regarding the microphysics of the atmosphere. So let's look at the aerosols. What can we see about the aerosols? Of course, we can make studies related to the sources of aerosols, how are these aerosols transported, the types of aerosols, and these types are coming from the multitude of information that we receive on all of the channels that type of channels that I presented. And we can also study the effects of the aerosols on, let's say, the atmosphere and the climate. So effects related to the visibility, the precipitation, the radiation budget, and so on. As I said, we can also look at the aerosol cloud interactions. We can study when clouds are formed and what are the aerosols that are present during the cloud formation. The dynamics, here I'm referring to the lifetime, and this is related to the sources of aerosols. The cloud formation, as I said, we can also study turbulence and of course the formation and the evolution of layers. Regarding the PBL, we can study the dynamics of the PBL and the interactions between the layers in the PBL and the interaction between the PBL and the surface of the Earth. The microphysics are more related to the aerosol type, and here we can look in depth. I'm sorry, something happened. I'm not sure that you can see my, okay, now you should see it again. So the microphysics is related to the aerosol type, and is related to the shape, the shape distribution, the types, the dimensions, and so on. But since this is an introduction course, we will not get into many details about this. So how can we study the atmosphere using the LiDAR? Of course, we can study this atmosphere by looking at different LiDAR products. So let's have a short introduction on the products that can be retrieved from LiDAR instruments. The primary products would be the range-corrected time series. So the time series of the collected signal, which is corrected with the range that the signal is coming from. And I will give some examples in the next slides. Another primary product is the backscatter coefficient. This is an optical product. It gives information on how the scatterers are backscattered, are backscattering a certain wavelength. The extinction coefficient, of course, the name tells everything about what this is, and not least the volume linear depolarization ratio, which gives information about how a certain volume of the atmosphere is able to change the linear polarized light into the two components, the parallel and the cross component. We also have some derived products. The first product is the LiDAR ratio, which is a ratio between two primary products, product 2 and product 3. We have the particle linear depolarization ratio, which gives information on how a specific particle is able to depolarize the parallel light emitted by the laser. So this information, it's very important to retrieve the aerosol type, as the LiDAR ratio is. And we also have as derived product advanced products for aerosol classification, like angstrom exponent, color ratio, and so on. So the main message here is that we have primary products and derived products. And in the single calculus chain, our main goal is to set up correctly the primary products and then look at the derived products and see how our setup is able to retrieve these products correctly. As an example, this is actually the first product that I was talking about. This is the range corrected time series here in the upper part. This is the time series collected using the Raman depolarization LiDAR at Inouye at 1064. And in this plot, you can see that the axis is the time. The y-axis is the altitude, which goes in this case up to 7 kilometers. And actually the color it gives information of the amount of light collected from that specific altitude. So in this case, we have profiles, 1 minute profiles going at up to 7,000 meters, starting at 400 meters with a vertical resolution of 3.75. And just by looking at this type of product, we see that we have a lot of information that we can study. We can see the planetary boundary layer and the different layers that are in the first part of the troposphere, in the lower part of the troposphere. We see several lofty layers at different altitudes. We see clouds, formation of clouds here. We see turbulence, different turbulent effects. We can also state that the planetary boundary layer is we can say that, okay, the PBL is not stable. So we have a certain instability in the PBL, and many more, depending on what we are trying to look at. But the main message is that we have a lot of information even from this primary product coming from the LiDAR instrument. In the lower part of this slide, you can see the volume depolarization ratio. And just by looking at the time series, the range corrected time series and the volume depolarization ratio, it's clear that we can distinguish different type of layers that we detected in this case. For example, the layer at 1.5 kilometers is not visible in the volume depolarization ratio, but the layer at 5 kilometers is very clearly visible in the volume depolarization ratio. Why? Because the volume depolarization ratio gives information on the shape of particles. Yeah, and just by looking at these two time series, we can conclude that the layer found at 5 kilometers is a layer made up of non-spherical particles, while the layer at 1.5 kilometers is made up of spherical particles, because we cannot see it in the volume depolarization ratio. We can also understand that inside the PBL we have some non-spherical particles, but most of the non-spherical particles are found in the layer around 5 kilometers. The same discussion can be applied to the other example on the right. We see different layers. We see, let's say, a layer at 2.5 kilometers, and we see a layer at 4 kilometers. That's not quite that strong. Yeah, and we also see a layer at 3.5 kilometers. And if we look in the volume depolarization ratio time series, we see that the layer that is not quite visible at 4.5 kilometers it's really visible in the volume depolarization ratio, meaning that this layer is made up of non-spherical particles. In this case, we have 3 layers. Let's say all the layers are non-spherical, but with different degree of non-sphericity. So this, let's say, thin layer that can be found, can be seen in the range corrected signal, has truly non-spherical particles. So this non-sphericity is high because the signal, the associated signal in the volume depolarization is really high. It's compared to the layer that can really be seen in the range corrected signal at 2.5 kilometers. So this type of studies can be, let's say, made even on the primary products. But the real value of a LiDAR system comes when we are looking at the derived products or let's say main basic derived products and not the advanced, not even the advanced products. If we look at the particle linear depolarization ratio, at the extinction coefficient, or at the backscatter coefficient, just by looking at this, let's say, 3 products, we can retrieve information on the aerosol type found in a certain layer. Okay, this is not the topic of this course, but just to give you this hint, by looking at advanced optical products, we can study a lot, and we can see a lot in the atmosphere. So all these products, the backscatter coefficient, the volume linear depolarization ratio, the particle linear depolarization ratio, and the extinction coefficient, are products derived by using the single calculus chain that we will learn a little bit later how to set up. Okay, so we already have 1 hour of course, of this training course, and I would say that before going to section 2, the initial setup of the LiDAR instrument, we should have a 10 minutes break, and then reconvene here at now it should be 4 Central European time, and no, 2 Central European time, yeah, and 3 Eastern European time. So we should reconvene here in 10 minutes at 10 past 3 or 10 past 2. Okay? So we can continue, I think. But before moving on, I would like to know if you have any questions related with our discussion up to now. So no questions. Okay, that's good. But please, if you have any questions, at least for section 2, just stop me and we can discuss more. Okay, so section 2, it's about the initial setup of the LiDAR instrument, and I will start with the environmental aspects. Obviously, the LiDAR instrument can be placed either outside in case of weather sealed and temperature controlled, let's say, unit, or inside the laboratory. And for this, of course, we need to have a window that can be opened, and the LiDAR can measure by, let's say, looking outside the window, through that window. There are several technical aspects that you need to consider, especially when you have the LiDAR instrument inside the laboratory, because, of course, if you have it outside, then you or somebody else already figured out how to properly adjust the instrument, and that means that we will not go into that section. But inside the laboratory, it means that the instrument could be subject to different, let's say, environmental factors. So regarding the aspects that I would like you to consider when setting a LiDAR inside the laboratory are the temperature and humidity stabilization. This is, you could consider that this is, let's say, obvious aspect, but in most cases, at least the humidity stabilization is not considered. And I would say that in cases when the humidity is quite high, effects like aging of the optical components or damaging the high reflected reflection coating must be taken into account. So another aspect that you should look when placing this instrument inside, and for this case also outside, is the electrical grounding. I know cases, also in our case, some time ago, when this electrical grounding was not very good, and this caused different, let's say, different unwanted effects on the LiDAR profile. So the electrical grounding serves at getting rid of all the noise that can cause can enter in the detection of the LiDAR profile, and this let's say effects are usually caused by other instruments or other equipments that are placed next or in the vicinity of the LiDAR unit. Another aspect, of course, is how clean the environment is. Usually inside the lab, since you need to open the window, there is a risk of dust and bugs coming from the exterior to the inside of the lab, and I saw that we need to be really careful about the dust placed on the emission optics and inside the telescope of the LiDAR unit. Another issue would be UPS for critical components like the laser, and here I'm referring to the fact that while the laser is running, if you have a power surge, the cooling system will not work, and you could have, let's say, damage inside the laser head. So a good practice would be to use UPS for critical components like the laser. Obviously, for vertical pointing, you need a hatch. It would be very good to have an automatic hatch that you can open and close from the computer or from inside the lab. Another aspect would be to reduce the reflections inside the room, and here I'm referring to the reflections coming from the laser light emitted. Usually, when you emit the laser and you use the laser inside the lab, you will see that you have a lot of reflections, especially on the wall, because the walls are white, and white is most reflective. And one good practice would be to use black paint on the walls next to the LiDAR unit. Another aspect that you need to consider would be the direct sun exposure. Usually during the day, if you have a direct sun exposure to the of the instrument, you will have some temperature gradients on the laser structure, mechanical structure, that could affect the alignment of your unit. So it's better to limit this sun exposure as much as possible. Okay. Another important aspect required, of course, before setting the instrument or while setting the instrument is to know all the information there is to know about this instrument. So for the laser, you need to know a lot. You need to know the energy per wavelength, how well the emitted light is polarized, the repetition rate of the laser, divergence, what is the polarization plane of the emitted light for each wavelength, the diameter of the beam. If you have, for example, a beam expander, you need to know what is this beam expansion. You need, of course, to know the optomechanical aspects and all the aspects related to the geometry of the LiDAR unit. So you need the distance between the emission axis and the receiving axis for biaxial LiDAR unit. You need, of course, the emission design, how the light goes through and how the light is reflected inside the emission unit. The accuracy of your alignment. And here I'm referring to the accuracy of the alignment technique that you are using. And not least, of course, the receiver design. You need to know exactly what you have in the receiver and what each component, optical component, is doing and how. Regarding this receiver information, you need information about the telescope, the focal, the field stop, of course, the field of view, the diameter of the primary mirror, the type of telescope, and so on. You also need the information on the setup of the deprivation channels, because I told you that you emit the parallel polarized light, but you can collect the parallel and the cross. You can collect the parallel and the total. You can collect the cross and the total, or you can collect all three. It depends. So actually, you need to know this information, and you need to know how you separate these components and how you record these components. You also need information about the specification of your detection units, either the PMT or the APD. You need to know information about the interference filters for each channel that you're using. And not least, you need to know the specification of all the optics inside the receiver. So the specification of the mirrors, the beam splitters, lenses, and how the light is transferred through these components. Regarding the detection unit parameters, you need information like the dead time, discriminator, row range resolution, sampling rates, the number of beats the recording is made, the bandwidth, the count rate, the detection mode. So all this information is not only helpful to you, but it's also required during the single calculus chain setup. And of course, you need some derived parameters that either the instrument manufacturer or integrator will give you. Either you need to determine by yourself, and here I'm referring to the overlap altitude. That would be helpful when you analyze the data, and would be helpful when you align the LiDAR instrument. You also need the deprivation correction parameters, and this will be discussed a little bit later. But anyway, these parameters are based mostly on the specification of the optics and the specifications of the laser. And you need the deprivation setup information. So how is the light collected by the telescope? How is this light separated, and what exactly are the detection unit inside this deprivation receiving block made, and how are these components detecting the signals. Regarding this initial setup, of course, before optimizing the signal, we need to detect the signal. So we need to have the signal, and to have the signal, you need to align the LiDAR unit. And by aligning, I'm referring to the alignment between the emission axis and the receiving axis. And this can be accomplished by using a CCD, or by directly looking at the LiDAR signal and making the proper adjustments, or by using an alignment tool like the solutions that Lysel is providing. I actually haven't tested this type of alignment tool. I only tested the first two, but if anybody has experience with that, I think at least I will be more than welcome. I will be more than happy to hear their experience. This alignment, of course, is made by adjusting the position of the laser. So a technical solution to align this, to perform this alignment, is by adjusting directly the position of the laser in case there is no emission optics after the laser inside the emission unit, or by adjusting the steering mirror. So one of the mirrors inside the emission unit could be used as an alignment tool. And of course, if you have this mirror, it's easier to perform the alignment. The best way, of course, is by adjusting the position of the laser, because this means that you do not have extra optics inside the emission unit, and this leads to less errors, especially when we are talking about the specifications of the emitted light. This alignment can be performed manually or controlled from the computer. If you have the possibility to control it from the computer, it's the easiest, because your hand, it's a source of error, and usually this source of error will bring trouble. But this does not mean that you cannot perform it manually. It means that it will only be a little bit difficult. Second, after we obtain the first LiDAR signal, of course, we need the optimization of this signal. And when I'm referring to optimization, I mean the level of the signal. Usually, as an example, we try to obtain around 1/3 from the detection scale for the maximum peak of the signal. Usually for light cell detection units that most LiDAR units are using, except the Poly XT, we use the detection scale from 1 to 100 millivolts. And as an example, we would prefer to have a signal with a maximum peak at around 35 millivolts. And this can be realized by decreasing the signal when using neutral density filters. This optimization firstly serves as a way to reduce the waving effect, or the high gradients effects that electronics the electronic unit is doing when you have a high gradient signal. And the secondly is to reduce the background noise inside the LiDAR signal. So this optimization, it's let's say it's useful from different perspectives. After the signal level optimization, it would be good to check the noise levels for each channel. Usually for typical LiDAR instruments with light cell PMTs and the detection units and telescopes looking in the troposphere with a diameter starting, I don't know, from 100 to 400 or 500 millimeters. This noise level should be around 5 millivolts or less. And this is what we should aim for. Another issue would be the noise stability. Is very good to check this noise stability once you have this newly LiDAR instrument installed, because you could have surprises. For example, you could have another equipment next to the LiDAR unit, and this equipment could affect the stability of your noise. And by checking this noise stability, you can understand that you have a problem, and you can do the actions to fix this problem. As a measurement procedure, and this is a personal suggestion, because the measurement procedures that cars will distribute are not fully finalized, and some updates are foreseen. I would have some pointers, but before going further, I would like to mention the current measurement setup that you can apply. The measurement setup can be either made periodically. So actually the measurement can either made periodically, so 5 times per week with 3-hour measurements, and of course plus intense extended measurements during special cases, or continuous measurements. In the case of Inoi and in the case of Cluj, we have measurements made periodically. But as I understood, in case of the Czech Republic, we have, for example, continuous measurements. So depending on the setup, you can go either for one or for the other. For the scheduled measurements, of course, you know, and everybody knows that these measurements must be performed during clear sky conditions, or in worst case with high clouds. And we need at least 3 hours per each set of measurements. I would say that before each measurement set, at least for the first period of after a new system has been installed, you need additional dark measurements before each set. In case of Inoi, we have 30 to 60 minutes dark, but you can also use, let's say, 10 minutes or 15 minutes smoothed dark, in case you know that the smoothing procedure is correct, and you saw that for your Lidar unit, there's no difference between the extended dark and the smoothed dark. The data, I would say that the data must be stored in a very clear structure, so that the user or the operator can go and take and analyze the data very easily. And also regarding the deprivation calibration, this type of calibration should be performed as often as possible in case of new Lidar units, because this way you have an idea, you get an idea on the stability of the calibration constant over time, and how different factors like, I don't know, the alignment or instability, mechanical instability of your Lidar unit is affecting the calibration constant. This is just an example of a data structure that is used for INOE in case of periodically made measurements. So the data structure should be defined based on the implemented automatic data submission tool that every station is using. But in our case, for the current period, we use a folder structure for each set of measurements with a special subfolder for the dark. So each measurement set will be placed in a predefined folder with the measurement date and time, starting time. And within that folder, we have the dark, the D folder. We named the dark folder as D, but you can name it whatever you like. The idea is to know how you name it and what's there. As you can see, for each folder we have a subfolder named D, and each main folder is the date, year, month, day, and starting time, hour, and starting minute. If you are planning to place all the files in the same folder, you need to somehow mark which files are dedicated for, which files are belong to a normal measurements, and which file are related to the dark. So one way is to mark in the header if this is a dark or a measurement or a test or a depolarization calibration or whatever you're doing with your Lidar instrument. My personal opinion is that option B is more difficult to be handled for cases when the user is manually processing the Lidar, but much easier for users that are using tools and scripts for completely automatic data processing. And as a, let's say, information, I would say that CARS, the Centers for Aerosol Remote Sensing, is currently working on developing automatic scripts for data manipulation and submission to the single calculus chain. And this most probably will require that all the files are in the same folder, but this requirement would be necessary once these automatic scripts are deployed and not before. So if you have questions regarding this measurement procedure, please stop me at any time. Oh, okay, so now it's section 3. So we will go to the quality assurance tests, and before going to these tests, I would like to ask you if this information was clear, the measurement procedure, the initial setup of the instrument, and so on. So I would guess that if I do not have any feedback, so no news is good news in this case. Okay. It's quite early, so I would say that we could go to section 3, the quality assurance tests. We would have around 20 more minutes and then we would have a break. Okay? So why do we need these quality assurance tests? So first of all, to make sure that the instrument is properly aligned, to make sure that the instrument does not have some design issue, or that the instrument is not malfunctioning. So for this, we have developed during the years within firstly EarlyNet and now ACTRIS, we have developed several tests that are meant to test the quality of the data, and these tests are let's say mostly focused on the telecover, a relay fit, a zero beam test, the calibration of the depolarization, and the dark stability test. These tests must be performed periodically. For now, the suggested periodicity is twice per year for some tests like the telecover, the relay, a little bit more often for the calibration of the deprivation. I would say at the beginning, as I said before, before every measurement set, and then I would suggest once per month or something like that if the user sees that the calibration constant is really a constant and not and does not jump from one calibration to another. Of course, these tests must be performed every time the operator is changing the setup of the instrument. So every time the operator is performing alignments or upgrades or altering something on the instrument. These tests should also be used internally to adjust the alignment of the instrument and check for malfunctions. But also the test should be submitted to CARS and should be submitted in a specific format to validate the correct operation of the instrument. And for this, of course, you need a sort of a manual processing and submission if you do not develop some scripts or if CARS does not provide these scripts. In the future, CARS will provide some specific scripts to perform this submission and perform this, let's say, pre-processing for the specific format. But for now, this should be made manually. Further on, we will discuss the purpose of each test, how to perform each test. I will give you some examples, and I will show you how to prepare the data format. So what is the data format? So if you have questions, please stop me and place your questions. The first test, of course, is a telecover. And this test is usually aims to assess the alignment between the emission and the receiver, and mostly to check if this alignment is correct in the near range. The test is performed by sequentially covering some sections of the receiving unit, but this should be made only during stable atmospheric conditions. So I put here some pictures just to make these statements more clear. So as you can see in this picture, you have the emission unit and you have the telescope or the receiving unit next to the emission unit, and you define, for example, 4 sections. The section closest to the emission unit would be the north section. The section which is further away is the south, and the 2 sections in between are the west and the east. And the measurements are performed by covering 3 sections and leaving only 1 section able to collect the light. So actually, what do? We measure, we collect 1 profile for each of the sections. And for each section, a 1 to 2 minute profile must be recorded. Each profile must be marked according to the specific telescope section. So it's marked north, west, south, or east. And usually an additional measurement, let's say if you start with the north, then an additional north 2 must be collected at the end of the measurement set, only to validate stable atmospheric conditions. So what do I mean? So if you are performing the telecover as something like first the north, then the west, then the south, and then the east, at the end of the measurements, you should collect again the north signal, just to have a comparison between the first measurement set and the last measurement set. This would be a very good indicator to see if the atmospheric stability is sufficient to consider this test as valid. So if the signal coming from the first north and the signal coming from north 2 is similar, then you can use the test for analysis. If you see that north 1, let's say, and north 2 are different, so if you see different atmospheric layers, or if you see, for example, I don't know, a specific cloud or changes in the PBL, then you should know that the atmosphere is not stable, and you should disregard this telecover test, and you should have another telecover test once you know that the atmosphere is stable. Usually, to have stable atmosphere, you should wait just before the sunrise. This is the most stable atmosphere, and of course, since the telecover test also applies to the Raman channels, and usually the Raman channels are used only during the nighttime, then of course also the telecover test must be performed during the nighttime. So the best way is to wake up very early and either connect to your LiDAR unit and do this, perform this test remotely. If you have a remote way to cover the sections of the telescope, either you should go to the lab and perform this test. The good news is that since this test is performed only once or twice per year, it will not be such a difficult job for any operator. As an example, of course, when comparing the signals coming from all the sections, these signals must be normalized in a region where you know that you have a full overlap. So the geometrical limitations of the LiDAR unit are not affecting the signal. It means that once you know, for example, that the overlap of a LiDAR unit is, let's say, 500 meters, then the normalization range should always be above this 500 meters. At a first look, North 1 and North 2 signals must be similar. In this example, you have the LiDAR signals, not the range-corrected signals. And I would say that as a first user, as an unexperienced user, or if you look at this data for the first time, it would be helpful to also look at the signal as received and as collected by the LiDAR unit, and not the range-corrected signal. As tips, of course, I would say that you could look at the intensity. The east and west signals should be similar. In this case, these signals are almost similar. The north, as you can see, should be the strongest. Also, North 1 and North 2 should be similar. and the south should be the weakest. And as you can see, this applies very well in this case. And as a new user, I think by looking at this criteria, you have a first indication that the telecover test will show that the system is properly aligned. Regarding the maximum peak that we were talking about, the position of the maximum peak, the north should be the first one, so should be found at the lowest altitudes, and in this case we found the maximum peak for the north at almost 200 meters. South, the maximum peak from south, which is a green, at the highest altitude, and I would say that in this case it's almost 400 meters. But anyway, this maximum peak should not be higher than the theoretical overlap, full overlap that you received or you calculated before. For example, if I know that my Lidar has a full overlap at 500, the maximum peak for the south should be lower. East and west and the west should be in between, so between 200 and 400, and this is correct in this case. And east and west should be more or less similar with each other. This is a first indicator that the telecover, of course, is performed correctly. You can also look at the relative deviation of the signals with respect to a mean signal coming from the four sections. And what you can see in this plot is the relative deviation. You can see that all signals converge towards zero below 400 meters. And this is an indicator that the system is aligned so that the full overlap is a little bit above, let's say, 400 meters. Once you gain experience with this, I would suggest also to look at the range corrected signal, exactly what you can see above. But this would be only once you gain some experience on how the signal should look, how the range corrected signal should look, and what exactly the full overlap and the incomplete overlap means. So firstly, I would say only look at the raw signals, and if you see some deviations from these tips, then that means that the either the LiDAR instrument is not properly aligned, either the telecover test is not properly performed, and you should iterate a little bit just to check these aspects. Okay, in this section, I explained exactly what I did before, the information about the relative deviation that indicates the full overlap range. Of course, signals must agree with a predetermined threshold. In this case, we usually use 5%, just above the full overlap, because as you can see, once you go further away at higher altitudes, this deviation is increasing. And just for you to properly see and understand what the test is showing, I would suggest to smooth the signals so that the noise is not an inconvenience to you. Regarding the submission of the telecover test, so once you know that a good the system is properly aligned, or once you know that you have a good telecover, or if you see that it's impossible to obtain better results, the the test should be submitted to CARS. The measurements, of course, should be sufficiently smoothed over range or time, as I said, in order to keep the deviation below some, let's say, below some limits, so that you could have the means to understand what you are looking at. Non-normalized range-corrected signals are preferred to be submitted, and usually the dive measurement that is required for cars to process the telecover should be submitted, yes, but should be submitted with the relay. So this dark will not be required in the telecover. As a general remark, this test should have sufficient averaging time. I would say 2 minutes per sector, but this depends on the telescope size and also on the atmospheric stability. If you have a very good signal and you see that the stability of the atmosphere is not quite that good, then you could decrease this averaging time. Let's say 1 minute or whatever you consider okay. In case that you see that the atmospheric stability is low, but you really need to make this telecover test, then you can make several rounds of north 1, north east 1, west 1, and again several times, and then store this information in successive columns in the data file that you will submit to CARS. Regarding the data file, the data file should have a specific format, should be ASCII. The columns must be separated by commas because spaces are neglected. Decimal sign must be the point, at least 4 significant decimal digits over the whole range. And of course, line breaks, carriage return, plus line feed. As an example of a telecover file, you see here that you have, let's say, a header and then the data rows, the data columns, sorry. So in the header, you need the station ID, the system, information about the signal, because you will need to submit one file for each wavelength. Okay, the date and the time, and exactly what you provided in this data file. So the range and north 1, east 1, south 1, west 1, and north 1, 2, and then if you know the atmospheric stability, low atmospheric stability, you can repeat this and you can place them one after the other. Okay, so this is the information that I wanted to present for the telecover. The relay fit is the next test that we will talk about, but since I see that now it's 3 o'clock Central European time and 4 o'clock Eastern, I would suggest to have 10-minute break. And if you have questions, please feel free to ask. Okay. Okay, so I think we can continue. Okay, so further on, we should move to the Rayleigh fit test. This Rayleigh fit measurement is actually necessary to verify the far range alignment of the laser. And I will stop there. This test must be performed in normal, let's say, measurement conditions. I would say 1 hour of Rayleigh with at least 30 minutes of dark, or as stated before, smoothly dark. The test could be, of course, submitted in two formats: glued signals or analog signals. I didn't went into details, but usually the measurement, the detection of the PMT detection for each channel can be realized in two modes: the analog mode and the photon counting mode. Usually the photon counting mode is the reference way and the let's say the realistic way that you should perform the measurements. But to extend the range of the, let's say, the data range in for altitudes where the photon counting is saturated, and these altitudes, of course, are related to the lower part of the profile. Then one can use also the analog signal, but this analog signal cannot be used by itself, usually, or should not be used by itself. Should this analog signal should be glued to the photon counting signal. Usually this procedure is straightforward, and it's performed by the single calculus chain. If you would like to know how to perform this gluing, the best way is to use the procedure that the manufacturer of the detector is providing. For Lysel units, Lysel is providing a sort of a paper. I would say I would go further and say that this paper, it's more of a technical or scientific paper that explains exactly how to perform this glue signal gluing. And Lysel is also providing a tool, LabVIEW script used to glue the two signals in case you would require glued signals. Okay, regarding option A, option when you send the test as a glued signal, of course, this option requires glue signals with a dark subtracted for the analog. The gluing must be performed after dark subtraction. The submitted profiles must not be normalized. The signals should not be smoothed. The profile, the Lidar profile should be limited, let's say, to 30 kilometers. And the Rayleigh profile should go to 30 kilometers or as high as possible if it does not go that far. If in case this Rayleigh profile is will go, let's say, up to 20 kilometers, then up to 30 kilometers put blank values instead of values. And for the relay, use radio sounding data. In case of sending only the analog signal, the dark measurement can be applied marked as D. The dark measurement should be processed in the same way as the range corrected signal. So background subtraction, range correction, and so on. This signal is sent to check that the background subtraction is done in the correct way and to check if the users are performing the gluing in good ranges. Okay. Further on, we have an example, actually two examples, if I'm not mistaken. Yes, the first one, the one above, is for 355 nanometers, and the one below is for the Raman channel 387. As you can see, the signal is normalized to the relay signal. In both cases, the black vertical lines indicate the normalization range. And of course, to assess the relay signal, one must have access to radio sounding and or let's say ground temperature and pressure. So one suggestion is always have a history of the temperature and the pressure at ground level while performing the measurements. It's a very good practice, because even if you know that you have access to radio sounding, it could happen that during one day or a limited period of time of 1 week or something like that, the radio sounding is not performed. And then you would need this temperature and pressure to obtain the relay profile. I will not go into details about how to get a relay profile, because this is an advanced course. But if you follow Frodentarl 2013, you will have all the information required to retrieve this profile. Actually, the relay profile is the signal, the Lidar signal that comes from the molecules. And this profile is indicates that the Lidar signal is properly collected, so the Lidar is properly aligned, since usually the Lidar signal is a sum of the molecular contribution plus the aerosol contribution. That means that the Lidar signal, as you can see in the two examples, it's always above the relay profile. The relay profile is exactly what you see in red. The LiDAR signal is what you see with blue. Once you have a normalized LiDAR signal to the relay, this signal, this LiDAR signal should never go below the relay profile. Because the LiDAR signal, as I said, it's a sum of molecules, the contribution of molecules and the contribution of aerosols. If you know the contribution of molecules, of course, you know the relay, yeah? The molecules in the atmosphere are always there. So if the LiDAR signal goes below the relay, that means that at that range, in that range, somehow part of the signal is lost. And this is not caused by the atmosphere, it's caused by the instrument. This is the role of the Rayleigh fit test. Regarding the data format, this data format is, of course, similar with the format for the telecover. So ASCII, columns separated by commas, decimal sign must be point, at least 4 significant decimal digits over the whole range, and of course line breaks, carriage return plus line feed. As an example, you have here the header, station ID, system, the signal, date of measurements, time and duration of measurement, because in this case we need information about how long it took to obtain that signal, the location. If you use a radio sounding for the Rayleigh signal, it's good to provide the ID and of course the date of the radio sounding. We need the lower and upper Rayleigh height limits, and here I'm mostly sure that this refers to the normalization range. And then, of course, information of what is each column that you provide. Again, one file for each wavelength. So if you have questions about the Rayleigh, if not, we should go to the zero beam test. Usually we have an error in the trigger delay between the real laser output and the detection system start. So the system trigger, the zero beam, what we call. And this can cause a large error in the near range signal. So the most important job that a LiDAR system is doing is ranging. That means that the most important and the most accurate job that is doing is counting the seconds from which the LiDAR or the laser unit is emitting light and knowing exactly when the light is collected with respect to the moment when the light was emitted. And if this is not accurate, then the ranging, so the altitudes that I showed in the profiles are not correct. And to check this, we have developed this zero beam test. And this test should be performed by using a near range target with known distance from the LiDAR instrument. So if you know that from, let's say from the LiDAR instrument, you have an output window at 10 meters and you shoot a laser beam on the output window, you should have a spike at 10 meters. Or if you know that you have a sidewall that reflects some diffuse laser light at, I don't know, 2 meters from the laser, from the LiDAR, then of course you know that you should have a spike in the LiDAR signal at 2 meters. And if you do not have this, if you have this at 10 meters or you do not have it at all, then you have a shift in the zero beam. But you can also use a fiber with a known length just to take part of the laser beam and direct it inside the telescope. So if you have, for example, a fiber of 100 meters, of course, the signal coming from the laser through that fiber should be seen at by the LiDAR instrument at 50 meters, because the LiDAR instrument thinks that the light was scattered at 50 meters above it, so that the total distance that the light is traveling is 50 meters to the scatterer, to the target, and again 50 meters back. So you can use this type of tool to see if the LiDAR instrument indicates correctly the height of the target. I don't know if I was clear. If not, please stop me. If I was clear, I will show you an example. For example, I used this fiber, optical fiber. I placed the optical fiber on top of the, with this cover on top of the telescope. We have the optical fiber above this cover. One end of the optical fiber is going inside the telescope, and one end collects part of the laser beam. Yeah, and I know that since the length of the fiber is known, I know that the real signal, the spike that I should get, should be, for example, at the 11th beam. Yeah, and since the range resolution is 3.75, I can determine exactly the altitude that the LiDAR indicates. And in this example, for example, you can see that for the 532 analog, we have a spike, the maximum peak at 12, and it should be 11. And for 532 photon counting, I have the maximum peak at 2 and should be 11. And since I know the deviation from what I should get, then I can make the correction afterwards. Of course, I can shift the signal in the case of photon counting to the right by 9 beams, and I could shift the signal from the analog to the left with 1 beam, and this way I can correct the signals. If you do not have any questions, then I would like to go a little bit further to the deprivation calibration. For this test, let's say, or for this calibration, it's a good practice to read and to look at these 3 papers that were submitted in the EarlyNet special issue from AMT in 2016. And this would give you a very clear view on the procedure to perform this deprivation calibration. Let's look at some definitions either way. So firstly, we have the calibrated signal ratio. So it's a ratio between the signals collected by the telescope, so the parallel and the cross component, that it is usually, let's say, collected by separating the components using a beam splitter cube that reflects one component and transmits the other component. And since by aligning differently this cube, you can have the transmitted as a parallel or the transmitted as a cross, then for generic purposes, we call the 2 components the reflected component and the transmitted component. So the calibrated signal ratio is a ratio between the transmitted and the reflected component multiplied by a calibration constant. This can be written again in a different form, can be written with respect to the polarization parameter and some calibration or correction parameters that we actually need to know to perform and to analyze the data. And these are these G and H parameters. And the polarization parameter can be determined by knowing these G and H parameters, and of course by knowing this calibrated signal ratio. Once you have the calibration, once you know these calibration correction factors, then, and of course, once you know the signals, you can determine this calibration signal ratio and you can determine the polarization parameter. Once you have this polarization parameter, of course, you can obtain the volume linear depolarization ratio and the particle linear depolarization ratio, which are two of the most important parameters when we are referring to the depolarization, the linear depolarization inside a Lidar instrument. So to retrieve the calibration or correction parameters, you need periodic calibrations. I would say once per 30 days should be sufficient. In the moment that you know that this parameter is stable. But you also need some technical information about the optics and the laser to assess other parameters like the G and the H parameter. Regarding the periodic calibration, for this calibration, two measurement sets are required at plus 45 and minus 45 for the two components, the parallel and the cross. And how do you accomplish that? You accomplish that by rotating this cube, let's say, at minus 45 or at plus 45 from the original position. Or you can realize that by rotating the polarization plane of the collected light at plus minus 45, or you can obtain this by rotating the emitted light at plus minus 45, or obtain this by filtering using a polarized linear filter inside the receiver unit placed at plus or minus 45. And this procedure is mostly explained in this paper. It's quite an extended set of information, but usually from the practical point of view, once you have a calibrator inside your LiDAR unit, you just either move the calibrator manually to plus and minus 45 and perform the measurements, or you can do it remotely from the computer if you have this option installed. For this calibration, after you get the plus and minus 45 signals for the parallel and the cross in this example, and once you have also the dark measurements, the data should be converted and submitted to the single calculus chain to retrieve the calibration constant. This will be shown further. For the assessment of the G and H parameters, it's very important to know information about your LiDAR instrument. once you know a good set of information about the laser, the emission optics, and the receiving optics, you can use a Python script developed by Volker. You can use this link to download it. And this script will provide you with this G and H parameter. Of course, once you have this script, you must fill in instrument parameters and system setup in the system settings subfolder. This, of course, this part cannot be included in the introduction course, and this should be made in a hands-on training. But in a few words, the user must fill in the laser beam polarization, the emitter optics information about the attenuation, retardance, the rotation of these optics. We refer to a predefined axis, the rotation of the laser polarization defined with respect to a predefined axis, the receiver optics information, the information about the attenuation, the rotation of the optical setup, the retardance, and so on. Information about the polarizer beam splitter cube, because also this cube is not perfect, and you also need some information regarding this. You also need the information about how the calibration is performed and where the calibration is placed with respect to the let's say receiving optics, if this is placed in front of the receiving optics or before the receiving optics or at the emission optics, or whatever setup you can have. So all this information is filled in this settings file, and then you immediately obtain the G and H. Okay, so once you have the G and H, and once you have the calibration constant measured with the actually retrieved with the single calculus chain, you can process the depolarization products. An additional K parameter will be provided with this script, and this K parameter is used to retrieve the total signal from the two parallel and cross components detected by the Lidar instrument. So this K parameter is also important, and I want to mention that G, H, and K parameters, these parameters will be submitted to the single calculus chain during the setup process, and also after the setup process if something is changing in the Lidar setup. Okay, do you have any questions regarding this section? If not, then we can actually move on to the single calculus chain. Okay, so section 4, the single calculus chain description and initial setup. For let's say complete overview of the single calculus chain, I would suggest to look at the paper written by Giuseppe D'Amico. That is also part of the IMT special issue, Alien special issue, was published in 2015, and gives, as I said, a full overview on the single calculus chain. So what is the single calculus chain? This is a centralized tool for the automatic analysis of LiDAR measurements. And as a practical note, the user must contact CARS and RS for the registration to the single calculus chain interface. This will take some time, so it's better to do this registration sometime before you are planning to use this single calculus chain. You could receive a request to fill in TNAs or to provide more information, and this process can be extended. The users should also consider to register to the forum of the community, the LiDAR community, and this forum includes information and issues and solutions and bugs on the single calculus chain interface. And it's a sort of a wiki for the single calculus chain. So it's very important to have access to this forum. Once registered and logged in, actually accessing the single calculus chain address, which is this one, you will be welcome to the single calculus chain. Right now is version 5.2.3, but depending on the moment you register, this version can change. You have a login button, and you can use the credentials to go to this to go to your, let's say, site, to your setup. Once you have logged in, you have the station admin section that is used to set up the single calculus chain. So you have the site administration, and more or less at the end of setting up the single calculus chain, you would have gone through most of these subsections. So this is a process, and it will take you, I don't know, several days to finalize everything. So the main sections of interest are the stations section, the telescopes, the lasers, the laser emission lines, channels, products, LiDARs, LiDAR versions, and LiDAR configuration. And we will go through each one of these. So the stations. Initially, you will have to define a new station, name, ID, institute, acronym, the coordinates, the PI information, and all sorts of information, affiliation of the PI, phone, and everything. Once you have this filled in, you can then move on to the telescope sections. If you are just starting with a single calculus chain, once you go to the telescope, you will see a blank table, but you can add a new telescope. And once you press add telescope, you have a new menu that asks for some additional questions about the telescope, the station that the telescope is assigned to, the type, diameter, focal, and so on. So all this information will be required for you to know. Not all the information should be filled in. You have some crucial information and some sections that you can leave blank. Once you filled in everything, you save this telescope the interface will tell you if it needs additional information or not. Okay, once you have a new telescope defined, or your telescope defined, let's say, you can go to the lasers. The same thing applies to the laser. You could add a new laser and then fill in all the required information, the affiliated station, the manufacturer, model, repetition rate, pulse energy, this is total, and so on. And then you can move to the next section, the emission lines, because each laser could emit one wavelength, two wavelengths, three wavelengths, four, and so on. And for each emission line, you need to choose the laser that you already defined, and then start filling information on that specific line. For example, wavelength, energy, length, polarization, diameter, divergence, and so on. Once you have this, you can then go to the LiDAR section and add a new LiDAR. You will associate this LiDAR to a station. You will have a name for this LiDAR, the PI, and the name that will be used in the quick looks site for associated with this LiDAR. Then go to the LiDAR versions, add a new LiDAR version, and in this version, you will be asked to write the start date from which this version is valid, and the stop date from which this version will stop being valid. And for each LiDAR version, of course, you can add a set of channels. No, actually, no. Once you have the LiDAR version, you stop there and go to the channels section and add a new channel. The channels, one second, okay. Okay, okay, still hear me? Okay. So in these channels, once you add a new channel, you will be asked to assign a string ID, a name of this channel, a telescope, the telescope that you already defined that is associated to with this channel, the laser associated to this channel, and then all the information required to set up this channel, like the wavelength, emission wavelength, the interference filter center of the in the receiving optics, the additional information on the interference filter, the field of view, and so on. So here you have a lot of information, as you can see. This is spread through these two examples. Once you have all your channels set up, then you go to the products section and you add a new product. The products that you can add inside the single calculus chain are the Raman backscatter, the extinction, the Lidar ratio and extinction, elastic backscatter, linear polarization calibration, Raman backscatter, and the linear depolarization ratio, and elastic backscatter and linear depolarization ratio. So these are the products that you can add. And here you have an example. For example, here in this example, I show you the elastic backscatter setup. You will be asked to define the product type, in this case, of course, elastic backscatter. You will have some additional information on how to use the channels for this product, and this let's say these criteria are defined in the use case, and the different use cases for each product are defined in inside the let's say single calculus chain interface. You just go to the user manual inside the interface, and you look at the use cases for this specific product. So for example, for the elastical backscatter, if you're using two channels, the 542 photon counting and the 532 analog, then a predefined use case that uses these two channels is the use case 1. If you go, for example, to use case 0, I'm guessing that you will only have one channel, which is a 542 analog or the 542 photon counting. Yeah, so according to the number of channels, you should set up the use case. Then you should connect this product to system ID. In the first setup of the single calculus chain, you will not have yet a system ID, and you should leave this blank and move forward. And then when you'll have a LiDAR version, you can add this product to that LiDAR configuration version. Afterwards, you will have some information regarding the error thresholds, the detection limits, minimum height, maximum height, vertical resolution, temporal resolution, type of interpolation, and I would move on because this is quite a lot. You will have to fill in the way that the single calculus chain should retrieve the elastic backscatter profile, the way the single calculus chain calibrates the backscatter inversion, and so on. So you have a lot of information that you need to fill in, and for each parameter that you enter there, you need to know exactly what to enter there. Okay, once you have, let's say, one product or several products configured, you can then go to the LiDAR configuration and add a LiDAR configuration. A LiDAR configuration will be a configuration in which you define products that this configuration should provide the user with, and these configurations are the parameters or the reference IDs and reference configurations that you use when you call the single calculus chain to process, let's say, a set of LiDARs. So you actually tell the single calculus chain, okay, I want to process this set of data with this LiDAR configuration. So this is the main, let's say, the main output that you will require. If you do not get to this point, you will not be able to process the LiDAR data. Okay, regarding this configuration, you will be asked for a lot of information, pointing angle, extra features, the channel connections, and you see that the number of channels for this example is quite high. The product connection, so here you have to also connect the products that you already defined. So all this is already defined, otherwise you cannot add them. And of course, other type of products that for now is better to leave uncovered because I think it's already too much. Anyway, the higher product is it's a high resolution preprocessed data product that should be defined together with the other product and should be included in this extra section that you have in the LiDAR configuration. So after you have everything finalized, then you can go to the data submission. The data submission will not take too much because this data submission is for this data submission you will only have to set up some scripts and run them, and the scripts will send the data to the single calculus chain and retrieve the data from the single calculus chain. So regarding the requirements, you need Python 3.0 up to the current version, okay, and you need two scripts developed by Yanis Binetoglu. These scripts can be found at by accessing these two links that I mentioned here. Once you have these links and you have the let's say the archives, and once you install Python, you need to install these scripts. Of course, you need to copy the files, unzip the files, open command com, go to the unzipped folder, the first unzipped folder, run the install command. I use, of course, a simple command Python setup develop. And once the installment is completed, you repeat the same thing for the other package. Of course, you have several ways of installing these two scripts, and you can choose either. Depending on your experience, it will be easier or more difficult, but if you follow the instructions that I presented here, I think you'll have absolutely no problem. Okay, so once you have everything installed, then you have to set up each script. And first, we will discuss about the atmospheric LiDAR setup. For this, you need to go to the systems subfolder in the atmospheric LiDAR folder and create a folder with your LiDAR name. Copy a setup file from an existing LiDAR that already you can find in the systems folder and edit the file. For example, you have several files for our LiDAR reference LiDAR instruments. We have several files, but usually if this is a simple LiDAR instrument with only one depolarization and with only one depolarization, you will have two files, one to convert and send the depolarization calibration data to the single calculus chain, and one to send the actual measurements to the single calculus chain. Okay. Then I will present the two files that I showed you a little bit earlier. The first one is the measurement conversion file, and the second is related to the deprivation calibration conversion file. And here you have a header with a system, laser pointing angle, coordinates, and so on. And then you have the channels, the channel definition. And here you have to define the type of channel, what channel it is, the ID that the single calculus chain has provided for that channel when you created that channel, and some basic parameters that you need for each channel. The background low and high. This is a range where the background is subtracted from the number of shots, usual number of shots, the Lidar ratio input. If you do not know it, just put -1 and define this in the single calculus chain interface and the range of the data acquisition. And this should be filled in here for each channel. So depending on your Lidar instrument, this file will be larger or smaller. Okay, the same thing for the deprivation calibration conversion channel, but as you can see, for the deprivation calibration, we have +45, +45 for the two, and in the lower part, of course, you'll have also the -45 and -45. So for let's say for deprivation calibration, you would require 8 channels. So you have, for example, for the parallel, the analog +45, the photon counting +45, the analog -45, and the photon counting -45, and the same for the cross. So you have 8 channels. Once you have this completed, then let's say then you can actually run the script to convert these the measurements that you have to the required format for the single calculus chain. I forgot to mention that these two scripts developed by Ioannis have two different purposes. The first script is designed to convert the Lidar measurements to the required format that the single calculus chain requires. And the second script is used to send the measurement file to the single calculus chain, wait for the processing to finish, and then download the data to the local computer that is using the script. Okay, so as an example, because usually examples are really good in this type of, let's say, discussions or trainings. For the case where the measurements are stored in distinct folders and the dark files are stored in a D subfolder, exactly like the setup described for Inoue. The usage is quite simple. Just copy and run a batch file in the measurements folder. The batch file should contain exactly what it is written with the red color. So if you use a batch file, then this file will know how to check for the files and take the files and convert the files. The only requirement in this case is that you go to the correct configuration file, of course, whatever you have, and that your files, the measurement files, start with the letter L. If they start with a different letter, of course, you can update this script. But usually, for Lysel, you have the R or whatever you have. It depends on how you set up the acquisition software. Okay, so this example was made for the measurement file, of course, for the depolarization file, because you also need to convert this depolarization file. You store the depolarization files, the two depolarization files, in a folder. You name the -45 measurement M45, and you name the +45 measurements P45. And the other files in this example are considered dark, but for the script to look at for the dark, you need to rename these files starting with letters R and N. But you can, of course, as written here, but of course you can do you can update this script according to your needs and your way of defining these files. So once you have everything in the same directory, the MP45 and also the dark files or file, you just copy and run the batch file in this measurements folder. The batch file should contain this information. Of course, you need to go to the parameters for the depolarization, and of course you need to see how you define the dark measurements, how you named the dark measurements. And once you run this script, at the end you will see a new file, which is a netcdf file with the extension NC, that should be submitted to the single calculus chain, and the submission can be made manually by going to the interface and uploading manually the file, or by using the second script that I will show you in the following minutes. So the second script, named the single calculus chain access, is defined. It's used to upload the Lidar data and download the output file to the local computer. After you installed this script as showed previously, you just edit, for example, the setup YAML file, and fill in the credentials that you obtain for your Lidar station, the credentials that the single calculus chain is providing to you to log in. Once you have this, of course, you go to the measurement file, copy the batch file that is dedicated to sending the data, run the batch file, and you will have everything, let's say, downloaded to your computer. The download directory that the single calculus chain output goes to is again defined in the setup YAML file. For the depolarization file, the same procedure, just copy and run this batch file in the measurements folder, and you will have absolutely no issue. So you will obtain all the required information and processed, measured single calculus chain optical products and much more. if, of course, the single calculus chain returns an error. For example, you didn't define correctly one parameter, or you made a mistake, then you will not be able to retrieve anything, and you'll have to go to the single calculus chain interface to look at the error and then try to deal with the error. And this is where the single calculus chain forum comes into hand, because you can search there for similar errors, or if you do not see and you do not find a similar error there, you can place a question, and the single calculus chain developers that are part of ours will contact you and will answer within the forum usually, so that other users have access to your questions and their answers. That's why I said that the forum is quite important. It's like a wiki page for the single calculus chain, but not only. You'll find there a lot of information regarding the Lidar procedures, the quality assurance, and many other information that is important for your, let's say, Lidar activities. In conclusion, I would like to have some feedback. So I would like to have at least one opinion of the overall feeling about the steps required to run a Lidar station. So is it easy to operate Lidar instruments? What do you think about the quality assurance tests? How do you find the data conversion procedure? What are the skills, in your opinion, required to operate a Lidar instrument? Are Lidar instruments simple instruments that you can use? Are these instruments used by simply pushing a button? And how easy, in your opinion, is to analyze the data once you saw the examples that I showed? So would you like to give me some feedback? Yuri? What do you think?
Okay, so I think, do you hear me? Do you hear me? Yes. Yes. Okay. Hello, everyone. I think that the first time it's a lot of information, so it will really take time to get into this all. So it's really interesting. But it's more information, so it will take time, I think, to be absolutely familiar and to be proficient in this.
Okay, so it's a lot of information. That means that it's not quite easy to go through all these procedures, let's say, and all these steps. I'm guessing that also the quality assurance tests are not quite straightforward, and you need to do this procedure several times to understand what it is to be done, and to get good results. Regarding the skills, I'm guessing that you need some skills. You need to understand how a Lidar instrument is operating, and how to look at the data. I would not say that the Lidar instruments are very complex, but if you go into details, then things can get really complex. Regarding the analysis of the data, I would say that depending on what is the purpose of, depending on the purpose of your analysis, it could be a simple, straightforward analysis by just looking at the layers, or an in-depth analysis by looking at the type of aerosols, by optimizing the processing procedures and trying to find, I don't know, sources, the age of the layer, and why not the microphysics, information about the microphysics. So I would say that this course was just an introduction course, just to give you an overall idea. Of course, things could change in time. Things could be better in time. Things could be better explained or worse. I don't know, but I think the course it's a good starting point. So I would like to thank also Horatiu and the persons that contributed to this this course. And anyway, if you have questions, or if you want to give me your feedback, I will write my email. Please send me a message, and I'm more than welcome to, more than happy to send you my feedback. So that's about it. Thank you, and have a good evening.